Hello, everybody. I'd like to welcome everyone to the November meeting of the Fort Worth Astronomical Society. My name is Bruce Campbell, and I'm the president of the society this year. And I'm glad you all made your way down to the meeting room and fought the traffic. But we have a small crowd, but I'm glad you all are here. Let's go to the first slide. Get the PowerPoint. So welcome everyone. Oh, that's a repeat. Let's move on. So I wanted to find out if we had any visitors or first time visiting on the show. Well, we have a visitor back here. Let's go here first. Could you stand up and tell us who you are and how you found us? Oh. Okay. Now, did you say you took a 15-year break? Oh, 50-year break. Things have changed. So get ready for an exciting ride. Good. And you want to tell us who you are, where you came from, and very good. Yep. Okay, let's go to the next slide. How about any of our new members that have shown up here? Are they here tonight? Okay, well, we'll have to get them out to one of the public star parties that we have. Let's move on. So, in case you didn't know, our club is one of the older clubs, astronomical clubs in the United States. We have over 200 members and individual membership accounts, and that if you counted all the people that are associated with that, that's over 350 individual people. That's pretty great. We have a wide range of astronomical experience from. I get to say this now. I know a couple guys that are starting to get into interferometer stuff to take images of the moon, or excuse me, images of the sun. So that's kind of fun. And I've been asked to talk louder. Okay, I can hear it now. We have a number of people that are visual only, and then a growing number of people that participate in astrophotography. So you'll find answers to most of your questions. Just get on the e-group and ask a question, and you'll get multiple responses. I'm confident of that. We also take donations from the public and members. So if you wish to make a donation, especially at the end of the tax year, contact our treasurer at fortworthastro.com. Let's move on. So our bylaws define what our mission is of the club. One thing is to promote astronomy via public outreach. And if you paid attention to what happened over the last week or so, we've had numerous star parties that have been wildly successful. People at Dinosaur Valley State Park flocked in hundreds, maybe tens, but quite a few people showed up, and they had a very good night for astronomy. We also work to support groups that are interested in astronomy, everywhere from artists down to middle school kids. They're interested, and we supply them information. And then we promote building of astronomy instruments and make club equipment available to our members. Let's move on. So in terms of resource, we have a member's handbook. Needs to be edited or at least updated, but at least it tells you how to behave at a star party, and that probably needs to be tweaked as well. But it gives you good information on the club and how to behave. We have a couple of observing areas, starting with Thompson Observatory in Keene, Texas. Have no idea why I'm stumbling over my words, but that's me tonight. Most notably is the Rising Star observing area that we have. It's a dark sky site that the club owns. We have numerous pads out there, and we'll come back to that later. We also have club telescopes and eyepieces that are available for club members to check out in case they're just getting started and you want to see what equipment works best for you. And then we have several online resources that are available. This is our dark sky site. It's essentially a 5-acre plot of land, where 3.5 acres of that is an observing field. Numerous pads, a few buildings to help us store equipment and maintain the facility. And we also have a composting toilet out there for privacy in the green building. Let's move on. These are some of the telescopes we have, numerous Dobbs that are available, a few refractors, a bunch of Spit Cassegrains, and one of the last one, the MacCast that's available. Viewing's pretty good. Okay, let's move on. Our online resources run anywhere from the Fort Worth Astro.com on the internet to our Facebook page, to our YouTube page, where you can find recordings of this meeting and other meetings that the club has. And then we have our Groups I.O. Discussion forums, either through the group or in astrophotography. And then we also have a Zazzle site that you can order Fort Worth Astro merchandise. And Christmas is coming, so you might think of that.
Continue.
So if you do need additional information, you can, if you need information about the club, go to our website. And if you want to join our club, you can do that at the Night Sky website that's run by JPL in California. All right, let's move on. All right, so now's the time for our speaker, and I'll ask Sam to come up here and introduce him.
Hope we got connected and got him online. It's Dr. Bernhardt. I think I've got that right. I'm not very good with names, but he's associated with a lot of things. When he started telling me, well, what do you want me to speak about? This, that. He mentioned Mercury. I said, well, I haven't heard anything about Mercury. So he's going to be talking to us about Mercury. He's Department of Geology, University of Maryland at College Park, MD. I'm sorry, where's that? Maryland. If we got him online, take it away.
Hello, everybody. First things first, can you hear me all right? Yes, okay. And I think I need permission to share my screen in the Zoom, which I sent a request for a few seconds ago. So anyways, thanks for the introduction. I'm Hannes Bernhardt from Department of Geology, University of Maryland in Maryland. It's just outside of DC. We're very close to NASA Goddard. And yeah, I wanted to talk to you about a small planet that's often overlooked. It doesn't often get the limelight. So I'm very passionate about sharing my passion about the place. So thank you for giving me permission. I'll launch PowerPoint. All right, Mercury. Mercury has been the focus of a good portion of my research for a few years now. And it's a small planet packed with wonders, let me tell you. So let's delve right in. I had to, all right, okay. So this is what Mercury looks from the ground. I assume many of you have seen this or a comparable scene where Mercury is actually the true morning and evening star. It beats Venus. It's not easy to observe, as many of you might know. It follows very closely around the sun at just 0.3 AU. Venus has 0.7, so that allows for a much larger angular distance between the two. So Mercury is really tough to observe, and it's small on top of that, and it's much lower albedo than bright Venus. Nevertheless, you can see it in good viewing conditions. I highly encourage all of you to try it. It's a nice little challenge. Now, Mercury here in to-scale comparison with our moon and Earth is a bit bigger than our moon and has about the same gravity as Mars, but it has only about 14% of the surface area of Earth and only 5% of its mass. So that's despite the fact that it has almost the same density as Earth. You might remember that the moon has a much lower density than Earth. Venus has almost the same density as Earth and almost the same size as Earth, therefore it has almost the same mass. But Mercury, as you can see here clearly, is much smaller. So despite the high density, it has a lower gravity, twice the gravity as the moon, and is about the same as Mars. The nomenclature on Mercury is interesting. It follows, so the International Astronomical Union sets standards for naming features on the planetary bodies. And for Mercury, that scheme follows for its impact craters, artists, composers, musicians, poets. Other features, for example, tectonic features that we'll see later, are named after ships of exploration. So there's a Beagle, an Enterprise, there's a Santa Maria, and so forth. On earlier slides, Biodirector asked for people's equipment. So this is my equipment. The first space probe to visit Mercury up close was Mariner 10 in 1974 and 75 with 3 flybys. It is very difficult to reach Mercury, much more difficult than to reach Mars or even Jupiter. The reason is that Mercury is comparatively small, as we just learned, but it's also very close to the sun. So it is trying to hit a very small target next to a very huge target that tries to suck you in. So what you need to do is you need good braking capabilities, and that wasn't available in the 70s. Later on, we launched a mission, Messenger, which is an acronym for Mercury Surface Space Environment, Geochemistry, and Ranging, which was designed in a way so that it reads Messenger as an homage to Mercury being the messenger of the gods. There is noise coming from the Fort Worth Astronomical Society channel. Maybe get that muted. Thank you. So Messenger was able to enter orbit, not just fly by, because it had improved capability to brake, so to decelerate, so that Mercury, small Mercury next to the big sun, is able to catch with its gravity the spacecraft. And we are about to do that again next year with a European space mission that's called Bepi-Colombo. And that will deliver a lot of data that is complementary to what Messenger was not able to get. Messenger was focused on the northern hemisphere. It did not have a circular orbit, but an elliptical one that brought it closer to the northern hemisphere. Bepi-Colombo will be the other way around. So it's 2 very complementary missions, and the instrumentation is not identical, but there are some similar instruments, of course, including, of course, a telescope or a camera, so to speak, a camera with high magnifying capabilities. So in essence, these are telescopes mounted on satellites around other planets. Mercury is an oddball for many reasons. And this is one of the primary reasons. Because Mercury is so close to the sun, its own rotational period is in a resonance with its orbital period. That means 3 Mercury days equal 2 Mercury years. The result you can see here. There are fake sunsets and fake dawns, where the sun comes up and then it goes backward and to finally rise for good. This is because of that set resonance, where 3 days equal 2 years. That is a day, a single day takes that long for Mercury to pass. And it also has a comparatively elliptical orbit. In the grand scheme of things, it's still pretty circular if you compare it to other solar systems. But for our solar system standards, it's comparatively elliptical. Another thing that makes Mercury very peculiar is that if you look at this diagram, it shows a pie chart, and each different sized slice of pie or pizza is a cross-section through the planets shown here. These are called the terrestrial planets in our solar system, so all those inner solar system planets. Yes, Moon is a planet. We planetary scientists like to call it a planet. Earth-Moon is a double planet system. The terrestrial planets of our inner solar system are those that have solid surfaces and are the inner solar system, so we don't count asteroid belt or Jovian moons. Now, among these, Mercury is very odd. If you notice here, the yellow layer is the mantle, and the grays are the inner and outer cores. The mantle is usually what makes up most of the volume of the planets, if you look around, except Mercury. A very thin mantle and a humongous core. Mercury's core is bigger than the core of Mars, although Mercury is smaller than Mars. And it's almost 2/3 the size of Earth's core, although, as we learned, Mercury is much smaller than Earth. So compare this, for example, to Earth's moon, which has a much smaller core. So that makes Mercury very odd. And we believe that well, there are two theories. Mercury might have been struck in the early solar system. These things happen all the time. That's how we believe the moon formed as well. So the early planets were struck by impactors, which were almost as big as themselves. And so the question is really who struck who at that point. Anyways, a collision happened that stripped away the outer layers of Mercury. So imagine that more of that yellow used to be there, but it was just removed. There's also a new theory emerging that Mercury formed like that, and there was just not that type of material available in Mercury's orbit. And that's how it ended up being from the get-go. In order to find out more about that, we would need to bring or analyze samples in situ and land on Mercury, I'm afraid. Well, I'm not afraid. I would love to. But that's, for example, how we found out how the moon formed, because we have all these samples and landed missions. And for Mercury, as we just learned, we only have orbital data so far. And for the foreseeable future, unfortunately. One thing that Mercury lacks, which makes Earth very special, is plate tectonics. That is a process that is very defining for Earth, but it needs certain prerequisites that are not met by most planetary bodies, at least right now in our solar system. I don't want to go too much into the details here, but essentially, it's a density inversion problem. Something becomes cold and then sinks down. Fair enough. It's similar to the skin of milk you boil. that being the planetary crust. Now, Mercury does not have that, and that makes it similar to Mars and the Moon. Venus might have had, or probably had, plate tectonics in its past, but not right now, and not like Earth anyways. So this is important because this will affect all that I'm going to talk from here on out when we talk more about details on Mercury's surface. For any planetary body with a solid surface, there are 4 primary processes that can sculpt the surface. And that goes for all planetary bodies, from Io to Triton, from Mercury to Earth, from the Moon to Pluto, and extrasolar planets, as far as we know as well. All processes can be categorized into those 4 primary processes that take place. And then it's just a matter of which processes dominate and which are not possible. But any process that can sculpt the surface of a planetary body in our solar system falls within these 4 categories. The most prevalent and ubiquitous one are impacts. We see them everywhere in the solar system. Impact craters are found on virtually all surfaces of the planetary bodies in our solar system. Earth doesn't have as many because of the last slide, plate tectonics, which is a rejuvenation. Like Earth gets facial surgery every few hundred millions of years that removes everything. That does not happen on the planets that do not have that. That includes Mercury. Another defining process is tectonism, where the crust deforms under stresses. It gets either squished or pulled apart or sheared. That can be caused by cooling, by tides, or density inversions like plate tectonics. It's a form of density inversion, as I said. Volcanism is the 3rd category that sculpts the surface, and that is caused by thermal convection from internal heat in a planet. And as long as the planet has enough internal heat so that it can break through the crust and material from beneath can make it to the surface, then volcanism is possible. The last one is so-called gradation. That means any recycling process on the surface that happens close to the surface and doesn't involve material coming in from outside or from beneath the crust. So these are processes driven by gravity as well as volatile cycling. Erosion and deposition by wind, water, ice, or life forms, like on Earth, life forms, humans, but also trees, all kinds of life forms affect and sculpt the surface. Glaciers do, rivers do, wind does, but also pure mass wasting, where material just falls down, landslides, etc. Just to give you an idea, so all of these processes are well known from extremely realistic Hollywood documentaries. So all of these processes are the stuff of drama, so to speak. There's no process that is more important or less relevant than the other when it comes to Earth. When it comes to Mercury, though, there's some things that we have to cross out that are not possible on Mercury. As we just mentioned, plate tectonics does not happen on Mercury. The density inversion, as a cause for tectonism, has to go. We still have cooling and tides, though. As for gradation, erosion and deposition by wind, water, and life forms has to go. Ice, we'll come to that. You might be surprised by the planet that is closest to the sun. And all the other processes, impacts, volcanism, they are just as possible and prevalent. And impacts even more so. So here we have examples of landforms formed by either of these 4 categories. We have a crater We have a thrust fault, which is the result of the crust, one portion of the crust being pushed on top of the other portion of the crust, so it buckles and forms this thrust fault scar. And then we have a crescent-shaped depression that is a caldera, a vent, where volcanic material came to the surface and an explosion occurred in a volcanic explosion, leaving behind this very irregular shaped depression. And then on the bottom, in the center, very small and a bit pixely, because these are small features, is a landslide. This is still a very big landslide, several kilometers in size. This little lobe-shaped, little mitten-shaped object in the center of that bottom image. But our resolution of Mercury's, of the images that we have of Mercury's surface that we can cover the entire planet with is just 220 meters per pixel. That doesn't sound too bad, but if you compare that, how many pixels for the entirety of Fort Worth would cover with that. So you couldn't analyze any details. Nevertheless, we do find a lot of things, and some selected areas have also been covered at higher detail, at higher resolution. Let's look at some impact features first. I mean, everybody here has seen a crater. I'm sure you trained your telescopes at the moon, maybe even visited a terrestrial crater, possibly meteor crater over in Arizona. This is a map of Mercury that in different shades of green shows all craters larger than 100 kilometers in diameter. So those are just the craters that are larger than 100 kilometers in diameter. Brighter greens are fresher craters that appear a little bit younger, and the darker the green shade is, the older, the more mottled, the more degraded these craters are. So there's lots of them. Mercury is the most densely cratered object in the solar system. Now, why is that? Here is the crater we seen earlier. This is a very fresh crater. And around it, you see a lot of smaller craters that are scattered around it. There are some other bigger craters which are older, but I'm talking about all these small pock marks around that fresh big crater in the center. The name of this crater, by the way, is Debussy, for the French composer. Now, this crater, when the impactor hit the surface, and that happens with any impact crater, it ejects material that forms a blanket of ejected material. You see that blanket around this crater, but it also forms thousands of small projectiles that form craters themselves. So in a ballistic flight, they are ejected and then re-impact the surface and form craters again, smaller craters. These are called secondary craters. That happens on the moon too, and all the other planets with impact craters. Also happens on Earth when impact craters form. On Mercury, it happens more for two reasons. Mercury combines a relatively high gravity, like a higher gravity than the moon, a gravity as high as Mars, but other than Mars, Mercury also has no atmosphere. So everything hits Mercury with full force, and these secondary craters can form without any atmosphere breaking these secondary impactors. So that is one of the reasons why Mercury has the highest impact crater density in the solar system. This is another global map. I'm showing you this because it's closely related to the impact crater story. This is a color map. So instead of, we have the camera with 3 channels, with 3 color channels, but instead of assigning those 3 channels to red, green, and blue to produce an image as it would appear to the human eye, we can assign these 3 color channels to spectral identifiers, where, for example, certain color ratios are indicative of certain mineralogies on the surface. And we can define these. So for example, this is what basalt looks like. And this is what volcanic glass looks like. Or this is what a more silicic, more granite-like material might look like. And then we assign that to the different color channels, and we can produce these color maps. In this case, you see that some craters have very bright light blue whitish rays. Those are very fresh craters. And that's similar to what you see on the moon as well, these long rays that can span the entire planet. So they look like little suns with rays emanating in all directions. Other craters appear blue. They have a blue halo or dark blue halo. And then there are some craters which appear without any outside halo or rays, but their floors are orange. So here's an example of one of those fresher rayed craters, light blue. Here's an example of a crater with a dark blue halo. Here's an example of a crater with a dark blue floor. And here's an example of a crater with an orange floor. That means craters are explosions that disrupt the surface from a projectile that ejects material. So it excavates the subsurface. Craters are basically free samples of the subsurface without us having to drill into the surface. And these different colors mean that different sized craters in different target areas expose and excavate different materials. So this color maps, combined with our knowledge of impact cratering, tells us something about the makeup of Mercury's crust. This is another image of Mercury's surface showing a lot of craters. In this case, blue and red refer to lower and higher areas. So this is a topographic map. The absolute elevation difference here is from dark blues about -5 kilometers to dark reds about +5 kilometers. So we're talking about an absolute elevation differential of 10 kilometers. You see that there's a very, very huge crater. That's an impact basin called caloris, which is just a Latin word for energy. So it's the energy basin. As in like the word calorie. That just means increment of energy. An odd name and an odd basin. If you remember what the lunar surface looks like, the surface of the moon has these big basins too, the mare. It's the face of the moon that stares at us with these dark areas filled by lava in the moon's past. Mercury has a similar setup with big basins filled up by plains of basalt, of volcanic material. However, here you see how the surface is warped, distorted, and there's a lot of tectonics that happened here, everywhere. Even uplifting the entire basin floor up here and down here, forming these broad waves in the crust of the planet. Getting out of myself, this is the next part about tectonics. What I was to point out here is you see craters of different sizes and different makeups depending on their size. You have a big basin, then you have a mid-sized basin that has a ring, and then you have craters, smaller craters that have central mounds, and then you have even smaller craters that do not or barely have any central mounds. Now, this is related to the physics that happen when the impact occurs, which I don't have time to get into details. Safe to say, there are different kinds of craters depending on their size, and they expose different materials depending on their size and how deep they reached and excavated and where exactly they occurred. Now, the segue to tectonism, as I just hinted at. Tectonism occurs all across Mercury. and it's one of the most heavily tectonized planets too. So Mercury really had to suffer. It's not just one of the most cratered surface, it's also one of the most tectonized ones, with most thrust faults and extensional graben. This is the same basin we just looked at, that Colores basin. Red are extensional and blue are compressional features. That means where the crust was pulled apart or pushed together. This is just to show you how intensely this area was mangled, once pulled apart and then pushed together again. And this is our model, why this and how this happens. And this is very similar to Earth. We have thrust faults that form because the crust is being compressed. Why is the crust compressed? Because Mercury, like all planets, is shrinking. That is, all terrestrial planets of the inner solar system. Icy moons are different. All terrestrial planets of the solar system are shrinking. Why? Things that cool shrink. And the planets still are in the process of losing heat that still stems from their original formation 4.5 billion years ago. The planets still have some of that heat, some more, some others less. But all of them still have some of that heat, and that slowly is lost. And in that process, they shrink. Mercury shrinks a lot. Why? Because it had so much heat, because it has such a big core, as we learned earlier. And that causes, like an apple that goes dry and wrinkles on its surface, Mercury forms the same kinds of wrinkles. Now, there are deep wrinkles, then there are more shallow wrinkles in its surface. They form different surface expressions, so-called lobate scarps or wrinkle ridges. There are various names to describe their shapes on the surface. And there's deep ones and more shallow ones that just form in the top layers. And some they're so deep they break the entire crust. And this is the dominant tectonic force on the entire surface, because the entire surface of Mercury is affected by this shrinking. It is a debate among us scientists right now by how much Mercury shrank, but it's anything between 2 to 7 kilometers of radius that the planet lost. This is a fault scarp that is called Grifo Rupes, named after an Italian vessel. That scarp cuts through that impact crater that you see here. That impact crater is called Villalobos. Some scarps and some craters are older or younger than each other. So there's craters that you see that happened on the scarp, and then there's craters that the scarp cut. So we can already, like a detective at a crime scene, piece together a story what happened here. So the crater Villalobos, the big crater formed, then the scarp formed, and then these smaller craters formed on top of the scarp. This is how we piece together a stratigraphy, history of the evolution of the surface. And you can map all of these, which was my recent science project that I worked on for the past few years. Here you see an example area. On the one side you see without the line work that marks all the different lobate scarps, these expressions of thrust faulting. And on the other side you see the map with them drawn in. I love this area because here's Bolzara crater. I don't know if there's any Queen fans here, but I got a crater named after Freddie Mercury on Mercury. That's his birth name. Anybody can name features, by the way. You just have to submit that to the USGS, who work with International Astronomical Union. They wouldn't accept Mercury as a name because they don't want a Mercury crater on Mercury. Well, I had to settle for his birth name. Nevertheless, we got it. This crater is 100 kilometers in diameter, by the way. So that gives you a scale for that image and how heavily tectonized the surface is. These scarps are everywhere, but they're not evenly dispersed and they have very different sizes. This is what is studied with the project that I called MERCATS, the Mercury Catalog of Shortening Structures. As you see, there are thousands of them. And unlike Earth, where a lot of the tectonics happen along the plate boundaries, all the thrust faulting on Earth happens within the Rockies, within the Andes, within the Himalayas and the Alps. On Mercury, it's more evenly dispersed because it doesn't have plate tectonics. The stresses are more even across the entire surface, but not quite even. You see that there's different orientations, and there's some areas where there are more and some there are less. This tells us something if we look at the average orientation of these things, and you see there's a pattern. Along the equator, they're more northeast, and along the poles, they are more east-west oriented. Although from the shrinking that I described, the stresses should be even everywhere and also isotropic everywhere, pointing in all directions. If something shrinks, it shrinks evenly across the entire surface. Here we see a pattern. This is on top of the global shrinking, there was a second stress, a second force that caused this tectonic activity. And this is the tidal despinning. As I mentioned earlier, Mercury has 3 days and 2 years. That's that resonance it formed with us because it's so close to the sun. And Mercury used to be spinning faster around its own axis. It got decelerated by the sun, the same way as the Earth gets decelerated by the sun and the moon as well. Days are getting longer on Earth. Days have been getting a hell of longer on Mercury. And that exerts force, a tidal force on the surface that is recorded in the orientation of these features as well, and that you can't see here. So this is just a snippet of a fresh off the shelf science that we are conducting right now with the data we have on Mercury. Next would be volcanism. This is caused by thermal convection in the interior, where hot material, like in a lava lamp, from the deep interior rises to the surface. It's called convection. Some of that material, if the conditions are right, if they make it to the surface, that is called volcanism. These vents, like the banana-shaped depression you see on that picture here, also can be found on the entire surface. I hope you can see these little red dots scattered across this global map. There are some clusters where there are more of them, especially around some of the big basins, but in general, you can find them everywhere. Again, on the Earth, volcanism tends to be concentrated at plate boundaries, except some exceptions like Hawaii, where it's intraplate volcanism, but for the most part, it's along plate boundaries. Again, there are no plates, or Mercury just has one plate. It has no plate tectonics. That means it's a more random process where volcanism occurs, where material from beneath makes it to the surface, but it's still not completely generic. It still happens in areas of crustal weakness. And these areas are often around big impact basins, where these big impacts weakened the crust and formed pathways through the crust. Back to that banana or crescent-shaped depression, this is a topographic map. Again, red is high, blue is low. And this shows you another very peculiar feature. Not just that this feature sits inside of a crater, which is not a coincidence, but also across the image runs one of those big lobate scarps that we learned about, talking about tectonism. These are associated for a reason. This color data, the 3-band color data I showed you earlier, and this shows you how they light up. Again, the color data shows us where there's different surface materials, and here it's material that came out of this volcanic vent, pyroclastic material, ash and cinder, that has a different color in our multicolor data than the surrounding area. In this case, the orange color corresponds to glasses. So we can calibrate our color channels in a way that the selected color channel, in this case the red color channel, is sensitive to glassy materials. Those form during violent volcanic eruptions. Impact glass are another version, but in this case it's volcanic glass. Some of you might know or seen volcanic glass. And any volcanic material contains glasses where they got quenched, the materials got quenched and cooled down very rapidly. And that's this halo around this banana-shaped depression. So an explosion happened with material being flung out. Why is that there? And how do we get material to the surface when, as I told you earlier, the entire surface is in a compressive state? The surface of Mercury is being squeezed together, as we learned by looking at these low-rate scarps. The surface is being pushed into each other. So it's in a compressive state. Getting anything through that is twice as difficult as under the best of circumstances. So what the ascending magma does, it looks for pathways, for zones of weakness. And there's two things that can provide them. And the two things that we learned about now. Impact craters, which smash the surface and create fractures that can reach very deep. And tectonic faults, which can break through the entire crust. And then the magma, as you see on this cartoon image, ascend along these pathways. And that's why we find a lot of these volcanic depressions, these calderas, these explosive volcanic vents, inside of craters, along tectonic scarps, and like you see here, both. You have a scarp that goes through a crater. These forms a double zone of weakness. The fracturing by the crater and the fault pathway of that tectonic fault. And that is then enough to overcome that compressive stress that squeezes the crust together and would instead prevent anything from coming through. But if these forces act together, it can enable material to come to the surface and cause explosive volcanism. Now that I said that, here's an exception. Here we see another one of these vents. This one is more like kidney shaped or something, or maybe a little rubber duck. And again, the colors show the orangish color is sensitive to volcanic glass, which is that halo around that irregular shaped depression. For example, here is an impact crater that's nice and round, and here's this irregular depression which cannot be formed by an impact. Instead, this is a compound vent. Compound because there's another little one inside of it. There's no scarp, and it's not within a crater. And these are less common than the ones that are associated with craters or scarps, but they do occur, and they're a bit of a head scratcher for us. There are various theories to explain them. There might have been a scarp there that got destroyed by other processes, and we just don't see it anymore on the surface, but in the subsurface it still provided that pathway. Alternatively, there might be a broader, thinner area of the crust that got warmed up by a hotspot underneath and caused the overburdened thrust to thin and enable stuff to come through nonetheless. But that is something that's still being actively worked on to fully explain. Volcanism doesn't just happen explosively on Mercury. There's also volcanism that is so-called effusive volcanism. That is more the type that you know from Hawaii, or lava, or Iceland, where lava flows ooze across the surface. And they can flow in lava rivers, and then they can pool in low areas and form vast lava plains. That happened on the moon. Those are the dark areas on the moon, the face of the moon, the maria. Those are big basalt plains filling impact basins. The same thing happened on Mercury. There's a difference though. This is one of the big lava channels on Mercury. Lava channels on Mercury are named after ancient ruined cities on Earth. So for Angkor Wat, this is named Angkor Vallis. Angkor Wat in, I think it's in Thailand, I believe. This is a channel that is almost 70 kilometers wide. So it is a humongous valley through which lava once flowed. The flow direction was from the northwest of the image to the southeast, pooling in this big crater down here, forming this basalt plain. And up here are more of those irregular depressions, these vents, which may or may not have been the source of this lava flowing here. We don't know. This is a big one. There are smaller ones too. So this is also fresh off the shelf research that I'm also still currently working on. These are smaller channels, and you have to squint and look really closely to notice what's going on here. That's why I included the maps next to each picture. Here is a lava channel, then it gets interrupted, and you see it again here, and then you see a little bit more here. And here is a very fleeting, intricate feature that is barely noticeable. You have to really know what you're looking for. You might be familiar with similar lava channels called rills on the moon. There, they can be very spectacular, very big. Why does the moon have a lot of it? And on the moon, you have hundreds of these. On Mercury, we only have a small handful, maybe 10, probably less. Some of them are really iffy. And they are very degraded and hard to notice. Why is that? Because on the moon, the kind of volcanism that formed these lasted for much longer. Whereas on Mercury, that kind of volcanism ceased over 3.5 billion years ago. The reason for that is here the moon is the oddball. Mercury is normal. The moon has some areas in its crust that are warmer because it has more radioactive elements there. That is because the moon's formation close to Earth that made it special. That affected where materials in the lunar surface ended up, and then also very big impacts. Mercury has the nearby sun, but that has not the big tidal force that, on Mercury as the Earth has on the moon. So the Mercury formed more even out, and it doesn't have this concentration of heat-producing radioactive elements in its crust. So volcanism, this type of volcanism that forms lava rivers and big lava plains, ceased much earlier than it did on the moon. The only volcanism that lasted a bit longer is the explosive one that I told you earlier, with these irregular shaped depressions, these vents that formed explosions and then halos of volcanic glass around them. But this is different volcanism than this. The last category, radiation, a broader term. Again, here's that feature. We find some of these where big chunks of a crater wall slided down in a big landslide, and you see this lobate, mitten-shaped deposit of a big landslide. This happened because that crater wall was at the angle of repose, and then due to the gravity, it started sliding down. This is also the reason why craters form these terraces, as you can see here and up here. Although these often form very shortly after the original crater formation, often just minutes after these big craters form. That's why we tend to refer to these terraces as an impact-related feature, although technically they're also mass wasting related. That's why they are usually filed in the impact category and not in the gradation category. This guy, however, formed much later, way after the craters formed. These are very fleeting and much smaller mass wasting landforms. These are granular dry flows that can happen on Earth too. If you ever been to, let's say, White Sands in New Mexico, or any dune field, any area on Earth where the ground is very loose, granular, and bone dry, you can initiate sand flows, where sand by itself just flows down the face of a dune or any sloped surface. These are called dry flows. We see them happening on Earth in dry environments, on the Moon, on Mars, and here on Mercury as well. They're just at the edge of our resolution capability, as you can see by the blurry images here. So these are wispy lines going from the top of a crater wall into the interior of a crater, down the inner crater wall. So these are granular dry flows. They are bright here too, and here as well. They are bright because they expose fresh material. As material sits on the surface, it is exposed to cosmic radiation and radiation from the sun. This darkens the surface over time. So whenever fresh material is newly exposed by whatever process, for example, these mass wasting processes here, it appears much brighter than its surroundings. It's exactly the same on the Moon. If the surface material is the same, that can be another reason. But in this case, we can say it's the same. And now comes something very cryptic. A unique feature to Mercury are the so-called hollows. These are also gradational landforms, and we're not 100% sure how they form. They have different stages of apparent freshness, we think. Sometimes they have these bright hollows, as you see. Sometimes they really don't. Here is one with a bright hollow, right next to is one without. And we think these are different stages of their evolution. This is a perspective view, and it almost looks like someone treated the surface with a blowtorch or something like that, and then blistering occurred. We think what happens here is similar to what can happen in permafrost environments on Earth, or a subsurface volatile on Earth that would be water ice disappears because it melts on Earth, and then it leaves behind voids that then collapse, and then they grow outwards because more and more material gets removed, melts away. This can also happen in karst environments like in Florida, where you get sinkholes all the time. Only there, they usually don't grow this steadily. They just happen at one spot and then another one happens somewhere else. Now, on Mercury, for the most part, I come to that, for the most part, it is not possible that there is water ice in the subsurface. Mercury is very hot. The daytime temperatures on Mercury reach over 500 degrees Celsius. So there is no spot in the subsurface that would be cool enough to allow water ice or most volatiles that we know to be frozen. There are other compounds, though, which might act similarly on Mercury. Certain sulfur compounds, for example, that could be trapped in the subsurface, and then when they reach a certain heat, a few hundred degrees Celsius, they evaporate, they sublimate, and then they leave behind these voids. Now, these hollows also like to occur in craters, specifically in young craters. While we do not believe them to be real volcanic features, that is, like this is material that came through the crust from underneath, they are related to these fresh craters, though, so there might be some connection there. We believe that craters in general expose from the subsurface these volatile materials, and then they are deposited in and around those craters. And then within a relatively short amount of time, for geologists, that's just a few million, maybe a few tens of millions of years, these volatiles sublimate, form these hollows, and then a few 100 million years later, no one knows what happened because it's all washed away, all degraded again because other impacts happen later that destroy everything. That's a process we call impact gardening that destroys everything on the surface given enough time. That's also how we can estimate the age of a surface feature. If it's very fresh, it can't be that old. So that's our theory anyways. Here's a map. They also occur everywhere across the surface, but there's tend to be some clusters. And those might be related to reservoirs of this volatile in the subsurface that fresh craters then excavate, bring to the surface where it can sublimate and form these hollows, leave behind these voids. This is the last slide. And it's also theoretically part of that gradation category. And I hinted at that earlier with ice, as in real water ice on Mercury. I just told you the surface temperature reaches 500 degrees Celsius. So how is that possible? Similar to the moon, you might have heard of that, there are craters close to the poles, the North and South Pole, whose interiors, whose crater floors are in perpetual darkness because the sun never goes far enough over the horizon that it can shine into these craters. Because the moon and Mercury have something in common, they are very upright. They're not as tilted as Earth. That means the sun never rises far above the horizon at the poles. If you have a deep enough hole, the sun will never shine in it. So we have areas like here, the crater Prokofiev at the North Pole, and smaller craters around it as well, whose interiors, whose crater floors are in perpetual darkness. And with that, I mean for billions of years, thousands of millions of years. The sun has not shone in them. And the important thing is, although Mercury is so close to the sun, and the illuminated surface around him is 500 degrees Celsius, because there is no atmosphere, the interior, these are perpetually shadowed crater interiors, never have temperatures above 70 to 80 Kelvin, minus 200 degrees Celsius, which allows a lot of volatiles to freeze solid. How does water ice get to Mercury in the first place? The dirty snowballs of our solar system, as you might know. Comets. They strike Mercury just as well. And when they impact, their volatiles get ejected, get dispersed, and just by sheer statistics, some of these molecules will hop along the Mercurian surface and sooner or later get trapped in a place that is so cold that they freeze solid, never move again. And that statistic process times billions of years gives you ice deposits that are visible in radar data. The top image is just radar data, where yellow is higher radar reflectivity, indicative of water ice. That was taken by the Arecibo telescope, rest in peace. It's amazing how the resolution from an Earthbound telescope can be on the planet Mercury. And then below the same scene, but now underlain with image data from the messenger probe. So that is quite amazing. I think that on Mercury you have possibly very extensive water ice deposits in these permanently shadowed craters. And with that, I close, and I'm happy to take any questions.
Dr. Bernhard, my name is Steve Kennedy. I've got two questions for you. Mercury's polar craters that you just mentioned, which include the confirmed water ice, given the extreme temperature swings and the intense radiation, do you think there's any plausible scenario, even a very remote one, where that water ice could support microbial life, or is that environment simply too hostile? My second question is whether or not people with Earth-based telescopes, astrophotographers, is there anything that somebody with a large telescope focal length of like 2,500 millimeters could conceivably image that would be of value? Thank you.
I take the second question first. When it comes to citizen science contributions to Mercury, I'm not aware of contributions for surface features on Mercury that are resolvable with amateur astronomy. Nevertheless, I know of citizen science contributions to Mercury science in the form of radiation measurements, where there were analyses of data from Earthbound satellites, but also the space probes that the scientific community has no chance to get through all the data. So citizen science can be essential to sift through the existing data. So we're not even talking about new observations, but analyzing existing observations. The one example I'm aware of is where the Mercury doesn't have an atmosphere, but just like the moon, it has a so-called exosphere, a very thin, fleeting, temporary atmosphere, comes and goes. And that elements of that were characterized in high detail thanks to citizen science contributions reanalyzing existing data sets from the messenger probe, but also from Earthbound observations. That is not so. That is a sort of answer to your second question. The first question, first of all, let me point out that we observed, when it comes to water ice in those polar craters, we observed they are confirmed is too strong of a word, but they're definitely indicated and highly plausible. What that means is the radar observations that we have are best explained by water ice at or near the surface. And our models of the thermal environment, if we put that in thermophysical models and model how cold are these craters, would indeed allow that to be the case. So behind the curtain, we hear the actor, and the stage is definitely set, but we can't be sure the actor is truly on the stage. So that is what I mean with, it's not exactly confirmed, but all our observations clearly point to that. Now, for life, if we imagine a setting where at or close to surface we have water ice, don't picture like a solid block of ice or something like a glacier sitting there, but more like icy dirt. Not even dirty ice, but icy dirt. The regolith, the pulverized surface material intermixed with a little bit of ice. That would be enough to explain the radar measurements. If that reaches into the subsurface far enough, it would reach, due to the geothermal gradient, it would reach a threshold where it passes over 0 degrees Celsius, and the water could become liquid, and would also be contained within the surrounding rock, so it wouldn't just evaporate away immediately. So in theory, it is conceivable to think of to have a habitable environment that would at least set the stage for microbial subsurface life. Do I think it's likely? I cannot answer that question. My first reaction would be probably no, but we learned better than that now. As I cannot repeat myself, it is conceivable that there is a habitable environment, but that doesn't mean that it has to be there. And even if it's there, it's a far cry from being inhabited. A habitable environment doesn't necessarily mean it has to be inhabited, but it is conceivable.
Thank you, Dr. Bernard. Is there anyone in the audience that'd like to ask him? I think we got time for one more question. By the way, I want to thank him, Dr. Bernard, because Bill just informed me we've been trying to get him for quite some time, but he's a very busy fellow. He's not just Mercury; he covers a lot of other things. So I want to thank him for hanging in there for us to get this time to have you come and present to us.
Feel free to follow the QR code on this slide, and you get to my university profile page, and you can have a peek at the other things I do.
Appreciate you. Okay, if that's all, thank you again. We'll let you go.
Thank you very much. I had a blast.
All right, so let's assume that it's 8:15. Let's take a 10-minute break and reconvene at 8:25. Okay, great. This man saved my life. I went to my car and was locked out, and he heard me pounding on the window and opened the door.
So you're saying that drawing was rigged?
Full disclosure. Yeah. All right, now we're going back to the white tickets. 480-6254. Last three digits, 254. So it wasn't rigged after all. How about that? Switching back to thank you. Switching back to blue, the last three digits are 033. 033. All right. The new guy. Fantastic. Oops. White ticket. I'll go with the last three digits, 243. White ticket, 243. Well, moving to a blue ticket. Ooh, 031. That sounds familiar. 031. You can come back up or move on. Okay, very generous. Thank you. Another blue ticket. Ooh, 003. All right. And the last ticket for tonight, blue ticket 050. 050. No one? Oh, we got one. Yeah. I already know he wants this one. Good.
I've never won anything before.
Well, congratulations. Bill, it's your turn. I'll get the light.
Thanks. Okay. Well, we know what the headline is this week. Active region 14274. And I had to look that up. I don't memorize that stuff. Yeah. Aurora Borealis in Dallas, once again. This picture is, if you go to the next slide, this is Stephen Kennedy's backyard at Possum Kingdom Lake. And it's so bright, photographically, but still you can see it reflecting on the water. Pretty cool. So, so I'm not covering any constellation this month because of the Christmas party in December. We're not having a meeting here, so I'm going to be doing this next 2 months, all the way to January, whatever it said in the previous slide. Next slide. So this is Glenn Frazier. He has an all-sky camera, and this is what he got. Oh, stand by. Obviously, north is up. So that was at 9 o'clock. It's 9:30. $11 and these were, it's like 60-second exposures at gain 300. It's kind of trippy. And then the moon comes up, and it basically stayed at that glow. And that's when I was like, I saw the chatter on my phone, and I was like, oh, I was in a dinner with a couple of my work peeps, and I got home, didn't see anything on the drive home because I wasn't looking, because I thought, oh, you know, that big 5.1, X-Class 5.1 that happened that morning, oh, it's going to be like 2 or 3 days, right? Isn't that how it usually goes? And like 15 hours later is when that CME hit us. So it was actually a remarkably fast-moving CME. And by the time I got home, it was midnight, and I was like, well, I'm going to try it. And I pulled out my phone, and next slide. I got the measliest one. This is the, but doggone it, it's red. There's red in that picture. It's Willow Park. This is Jim Catherine at his remote scope at the dark site. Patrick's in Arlington. That's pretty fantastic. And even Steve Yates in North Fort Worth got just like structure and stuff. It's just amazing that you know, you just got to have a CME just pointing right at us when that's going on. There was another one that actually happened, but it happened in front of Earth's orbit, so Earth's like moving towards it. So, you know, the speculation was, and I don't know where we're at with it, but it possibly could be a glancing blow, but otherwise probably not remarkable, certainly not like this. So, hey, 25 is still alive. That's the sun cycle, that is. Next slide. So bright comets this month. There's 6 of them. You got R2, 2025 R2. which is in Pisces. It's getting dimmer. I think that it's R2 that's actually breaking up. So there's actually 2 or 3 fragments of it now. 2025 A6 Lemon is in Ophiuchus. It's dimming. That was the big superstar. As you can see, this is Jim Pott's shot of it. I hope you all got to see it. Now this next one, 2024 E1, I'm not going to try and pronounce the discoverer's name. That one's around magnitude 8 and some change in Serpens right now, and it's getting brighter. This is the one that I've been talking about from earlier in the year. They're speculating that this might get to magnitude 4, well within naked eye visual in late January. So we'll be talking about that in that meeting. 210P, Christensen. It's getting a little brighter in Libra. It's not long until it starts to dim, but that's 2025 T1. You know, it's a little over magnitude 10, but I wanted to put it in because it was actually a relatively newly discovered comet. And that one's in Hercules. And then we've got 24P, which is 8.5 magnitude in Leo. So I told you at the beginning of the year that it's pretty much going to be unremarkable until the end of this year, and here we are, and there you go. And as always, I'm getting my information from arith.net is the place to go if you want to know about every comet that's going on that's worth looking at, or really any of them. Next slide. Yes, sir. Yeah, go back. Yeah, the green means that it's getting brighter, and the red means that it's getting dimmer. Yeah, next slide. Occultations and close approaches. You know, I'm starting to wonder if like Moon and M45 just like dance like this at every lunar cycle. I don't know, but there you go. The 3rd and the 31st, that's happening again. Patrick McMahon, always with great conjunction pictures. This one is Jupiter and Venus in March of 2023. Next slide. New moon in November is November 20th, which is, when is that? 2 days from now? Yeah. I'm ready to get our meetings out of new moon. Next slide. Uranus at opposition. So on Friday, November 21st, we're going to have Uranus all night long in the sky. It shines at magnitude 5.6 when it's at opposition. If you've ever seen it in a telescope, it's a nice little bluish-green disk. And if you've ever seen it, well, you can actually, if you got a good dark sky and a big enough scope, you can see a couple of the moons or more, maybe three or 4 of the moons. And photographically, you can see at least 5 of them. This is Voyager 2's last look at Uranus before it left it. Yeah, next slide. Saturn ring plane crossing. We've been waiting for this all month since the bust in March when it was too close to the sun for us to see. But fortunately, this particular Saturnian autumn, we get to see the ring plane crossing twice. I don't know how this works because I didn't look into it. I have no idea how this works, but apparently in 2038, when we get the ring plane crossing again, it's supposed to happen 3 times. And I don't know really how that works. So see you there. Let me see. After this, of course, we start moving towards winter with Saturn, and it starts widening until 2032 when it's at its most oblique to us. The edge-on technically happens on Sunday, November 23rd, so what, 4 days away, 5 days away? The rings all but disappear. And we're really close to it. I actually imaged Saturn the other night, and it's just a little bit tighter than this, but we're close to it, and it's perfectly placed in the sky. It's in the night sky. It's probably near transit right now, so it's good for us this time. This is actually Christopher Ashford's image. Actually, I think this was his first Saturn picture, so good job, Chris. Next slide. December's full moon is December 4th, and one of Glenn Fraser's pictures of the moon there. Next slide. Mercury in the morning, it's a theme. At greatest western elongation is on December 7th, and it's going to be 18 degrees above the horizon at sunrise. So we're all taking the challenge, all us imagers, right, to try and image Mercury this time, right? Everybody getting wound up about that? Okay. We'll see. That's right. Challenge accepted. Next slide. The Geminids meteor shower. So this is the best meteor shower of the year. It's not bad as far as the moon this year. I think I'm right on this. I think I fixed it. The year's peak is with a 24-day-old moon. Y'all feel free to fact check me. It's not going to hurt my feelings. It's a lot of information that I put together with these things. Saturday night, December 13th, through Sunday morning, December 14th. This particular footage, the video stopped, but that was in 2020, and I was in Bortle 2 skies in the hill country, and yeah, it was a pretty killer night. I just stayed up all night long and just laid on my back. It's great. CHR, sir? Sure. Right on, right on. I just bought a color all-sky camera, so I'm pretty stoked about having color. This was my black and white one. So yeah, so usually, at best, in dark skies, you can have a zenithal hourly rate of 120. So it's a very active meteor shower. I love this one. Next slide. Oh, but I recommend an electric blanket or something. You know, January's new moon is December 19th, and this is actually Preston Starr. I dug this one up. Preston Starr actually took a picture of the 2024 total solar eclipse. He was for all of you that don't know, he was a president of the club a while back, I guess. Next slide. Longest night of the year, 13.5 hours of darkness. That's what we all been waiting for. That's December 21st with the winter solstice, which makes the sun overhead where? On the Tropic of Capricorn. Good job. Next slide. Hygeia 10. I always like to feature at least the first 10 asteroids. This one's actually the 4th largest asteroid, but it was the 10th one discovered because it's got a low albedo. And smaller asteroids were actually discovered before that are just brighter. It's shining in Gemini at a magnitude of magnitude 11 to 12, and it's in opposition on December 22nd. Next slide. January's full moon is on January 3rd. This is a awesome moon picture by Mr. Robert Cargill. Next slide. Then there's the Quadrantids meteor shower. So Quadrantids is named after Quadrans Moralis, which is a now extinct constellation, so quadrant, and it's now a part of Boötes. But this one, I love this one. It's not great because the peak is actually, I think, on full moon. We'll know in the next slide. We can confirm that. And but the ZHR averages about 40 in a dark sky. I've seen this meteor shower with the moon up and laying down on my back in my backyard and with an electric blanket and having a stand holding this piece of cardboard to just like block the moon from my eyes, and it was still a great night. So these two, this and the Geminids, are always worth seeing no matter what the moon's like. Next slide. Oh, this is a statistic we don't hear about a whole lot, and I thought it was kind of cool to feature. So it's Earth at closest to the sun on January 3rd. Not that that matters to us. I'm not a big fan of the cold, so I'm really enjoying this week. But if y'all recognize this is the pale blue dot picture from 35 years ago. For all of us that like were, watched as, Voyager 1 was doing its thing, just like think, oh God, 35, okay, well, that's cool, whatever. Anyway, Earth at perihelion, January 3rd. Next slide. Jupiter opposition, little better shot of this planet. On Saturday, January 10th, Earth's going to be at 399 million miles, as opposed to the greatest conjunction that Earth and Jupiter have, which is 577 million miles. Now, this is significant because when it's at its farthest, it's at 31.7 arc seconds, and when it's at its closest, or at least on this one, it's 45.9. So, and of course opposition has it in the sky all night long. So the king is coming. Next slide. New moon. January's new moon occurs on January 28th. 28th. January 18th. Long day. Next slide. And so this is the final slide here. I want to know who stayed in this cabin and what you're going to buy, because this was a good time to be there. Anyway, this is a picture that TJ Harden took at 3RR, the club's visit to 3RR this year. I heard it was, well, obviously maybe not ideal conditions in the sky, but hey, double rainbow. So keep looking up. Thanks.
Turn the lights on.
I will turn the lights on. Watch your eyes.
So we're getting into the business meeting, and first up is the treasurer's report.
Thanks, Bruce. Good evening, everyone. Okay, our finances are solid, no question there. Current balance is just over $47,000. Notable transactions includes a $4,000 donation from one of our members and $1,500 revenues from one of our 1687 star parties. Moving down the page, our rising star development funds are currently at $2,200, and we have our next loan payment in April, $810. Any questions? Please be reminded that this and all previous reports are available in the file section of Groups.io. Thank you.
Thank you, Constantine. Okay, so I did want to say one thing. I guess we could do this in outreach, but I'll do it now. Juan Martinez was asked to speak at a get-together from folks from the Kin Folks House group. And after that presentation, they gave him a $300 honorarium, which he then funneled over to the club. So I'm always amazed how people who do good things are rewarded. And the note reads, Juan, thanks so much for doing the sky navigation activity for the closing of inner space. That's an activity they had going. I'm so happy to have met you through FWAS. You seem to be knowledgeable, and you're funny. And you're funny. Okay. So I thought, just want to recognize Juan for his good work there. All right, so the executive board met last week on Tuesday, early in the afternoon to accommodate Chris Ashford, who's visiting his mom in England. And I just to let you know some of the things that we're working on. The bylaws require us at our November meeting to start working on the preliminary budget for the following year. We had the initial estimates come in of what the expenditures and revenue may be. My task is to go out to the committees and take a closer look at those numbers and see if we can bring them down a little bit. I think our budgets are rational, but we don't always spend all the money that's in the budget, so we're going to try to bring down that to make sure our income and expenditures are closer than what they are today. Also in November, we discussed in the bylaws what are the possible changes either to corrections, think of those as typos or things that are now outdated, or updates. So far, we've only entertained one update, and that is to change some of the structure of the way the club operates. In years past, when the bylaws were first written and the organization was set up, we were a much smaller group. We didn't have any land, and things have changed in the last 50 years. We have a lot of things going on. We have numerous groups going along, and we're trying to figure out a better way of organizing the group so we report up through the board more systematically. That's the way I'm going to put it. So we're going to talk about that at our meeting in December. So I'm going to jump to the last item there, and that is the board has decided to meet monthly because we just have too much activity on our table, and we think that if we meet monthly, two things will happen. We'll be more productive, and we'll take only like an hour and a half instead of 3 hours at one particular time. I hope you're enjoying these unseasonably warm temperatures. We're moving in December, wintertime. We're not going to always see that. So if you're heading out to Rising Star, either on a work party or going to stay all night for astronomy, please prepare for the conditions. What the board's going to do is we're going to put in electric heaters into the bunk rooms, but we also suggest if you're going to overnight in one of the bunk rooms, bring a electric blanket. That's been talked about several times. And that way you can heat a smaller environment and not try to heat the entire bunk room. But our plan is to put heating, we're reviewing our electric heating options, but we're essentially going to put in a, what are they called? A heater. A what? Well, that's one of the brands, but yeah, we're going to put in a thermal, I don't know, but we're putting in a heater. That's the idea, a local heater. Sorry about that.
Can I just make a comment on the heater?
Yeah.
Those buildings are not built for conditioning. It's going to be a complete waste of energy. You're going to heat the air, it's going to go.
Yes, that's been the thought, but people wanted to have heaters. We've got heaters left over from last year still in the bunk rooms, and so we're trying to bring some relief. But we can take these comments back to the board. But because we have electricity in each of the bunk rooms, if you're going to stay the night, bring your sleeping bag, put a electric blanket in there, and you'll stay comfy warm. The room might be cold, but you'll be warm. And so we also looked at putting heating stations out on the observing field, and we didn't find any options that were good, so we're going to ban the use of propane tank heater attachments on the observing field. So we're thinking that it's just too close to too much of a fire hazard, and we're just going to go down that route. And then I covered the point where we're going to meet monthly to better manage our club business. So that's all I have. Any questions?
Bruce, Steve Kennedy here.
Yes, sir.
So I just wanted to point out to everybody who's watching that in our December Board of Directors meeting, we are going to be talking about a proposal that has been presented by one of the board members that I think is fair to say is somewhat controversial in how the club will be managing and supervising some of the people who I call department heads. For example, the people who do the star parties, the people who do outreach, all of the people who make the club function. There is a proposal that has been submitted by one of the board members that will radically change how those people are supervised. And so I recommend that anybody, if you care about that kind of thing, and if you care about how the board is going to be possibly changing how those people are supervised, I would encourage people to attend by Zoom the board meeting in December. I don't want to state my position on this yet, although you might be able to figure it out from my tone, but I think it's very important that people be aware of it and possibly attend the board meeting so you're aware of these potential changes. Thank you.
Very good. Thank you, Stephen. So there will be a Night Sky Network message that goes out that identifies when the next board meeting will be, as well as the Zoom invite. So if you're interested in that, watch for that email. Comes out typically the week before the meeting occurs. All right, let's go to the next slide. So I did not have any input for tonight, so let's go to the next slide. And any other business here from the club?
Couple things. I want to thank Charles Haggard I want to thank Tom Roth and Charles Haggard. We had an opportunity to use the meeting room at Rising Star last weekend for an APSIG meeting. Worked flawlessly. It was awesome. So it was myself, Jim McCatherine, and Peter T. Arena participated in an APSIG meeting with Dr. Glover from England, and we connected over the internet, had a big screen TV in there, and watched the presentation. It's just where the construction you guys have done out there is nothing short of phenomenal. I know I had scatterbrained visions of what we wanted to, or what I thought we wanted to do out there, and you guys have brought it together. It's really great. I just wanted to thank you for that. And I'm excited to report that the Charlie Mary Noble Observatory is operational. We got the rotation gear working, the shutter operates properly, and the shutter is solar powered. So you'll be seeing some images. We covered off about 8 images, 8 objects over the weekend. And so those will be published, but that's exciting news. We were hoping to have it ready for Cook Children's this weekend. We have it ready, but the weather's not going to cooperate. So anyway, there's going to be more about that in the near term. So thank you.
So Bob thanked the construction crew out there, which is good, and the round of applause was nice. I think we need, Bob, a round of applause for getting the Noble Observatory up and running. Good job. Any announcements?
And don't forget to include Sam and Ted helping us out.
On the doors? Okay. Yeah, it was a team effort. Let's move on. Is that a club asset, guys? Is it? Yeah. Maybe we'll get a backup. Oh. I, three slides away. It's, I think it's December 14th, 13th. It's either, it's Saturday, December 13th or 14th, whatever, 13th. Any other questions? I am bothered by the clock, though, in the room. I'm bothered by the clock in the room. It's an hour off. All right. Oh, and here it is. Here's the information. Same time, same place, different date. We're doing it the 13th, 2025. And then after we have dinner together, we'll do a voluntary gift exchange, which in years past has been pretty fun. If you decide to participate, bring a wrapped gift in the $20 to $30 price range.
And if you need even more encouragement to come, we're going to demonstrate the dome.
Okay. All right, next slide. So we're going into our monthly reports, and let's first start off with Patrick.
Well, it looks like our string of good weather's come to an end because tomorrow and Thursdays are canceled, so disregard those. Figure had it in at some time. So Saturday, I'm still looking at the forecast. I'm not sure what's going to happen there, but if it does happen, we have Fort Richardson. We were there in July, so we'll do another run for them this Saturday, but also one of our members, Charlie Ford, his group's going to be having a camp out over at Mineral State Park if anybody wants to help out a little bit closer, but again, we'll see how the weather holds out on that. Next. And then in December, it's the first, we got a school we've been to before. Then we'll be at the Nature Center on December 6th. We've helped them out in the past, had a pretty good turnout. Then we got another school on the 4th. And then our last Dinosaur Valley Star Party will be December 20th. And that should be it for the remainder of this calendar year.
Very good. Thank you, Patrick. Let's go into the Tandy Hills. As you can see, we do have an event scheduled for the 29th of November. And let's go to the next slide. There's more of the details. If you think that you might want to come out or just have any questions about the Tandy Hills, reach out to John McCrae. We do have a report on young astronomers. There really is no change in situation there. We're still negotiating the with the Y on the venue. Next slide. 1687. Bob.
So we had our fourth and last 1687 event a couple of weeks ago for the Pink Beret. It was a great evening. Lots of oohing and awing, I think. And we had I forget the comment, but it was really interesting. We could see it going, and then it slew right through power lines that we picked up in one of the scopes. It was quite an event. So we did 4 this year. They've asked us to come back again next year, and as an added twist over the summer, they may ask us to come out and do solar parties for the kids. So.
Tell them about your use of VAA.
Oh, yeah. So we tried something a little different. We set up an EAA workstation. I had my Red Cat out. And so Bruce had I think it was M31. We had a couple of objects where people would look in the eyepiece, right? And when you look in the eyepiece, it looks quite different than when we're imaging. So people could see the side-by-side comparison of what it looks like when we capture from a camera as opposed to the eyepiece, and people were quite impressed. So that was something new. I think we should do that for all-star parties. Hint, hint, hint. Yeah. Before I forget, there's something that's near and dear to me, is we're doing Cook Children's this Saturday, rain or shine. And so it'll be Mr. Velvet Voice, Bill Hall will be doing the presenting. And I'm just going to be a keyboard operator, and we'll have a telescope set up inside in the Hochberger Auditorium. It'll be from 6 to 8. That we know the weather is not going to cooperate, so we're going in with a slideshow. We may have some, if it's not raining, we may remote in and show pictures of the 2 observatories out at Rising Star. So it's just an exciting thing. The hospital system's looking forward to this, and it'll be a great. I'm sure it'll come off very well, and they're going to have us come back again. So it'll be a great partnership. But we're looking for 3 things: a good picture of the moon, a good picture of Saturn, and a good picture of Uranus. And the objective here is to get. Being in a hospital is not fun. Being in a hospital for a kid has got to be miserable. So my wife has been arguing with me about whether or not to do Uranus or not. It'll make the kids happy to be able to say it the way that they want to say it, so that's why we want to show it. So we're needing those 3 images. So if you could send them to me, that'd be great.
What if they ask, is this your Uranus?
No comment.
Do all these things get put on our calendar? Because it'd be nice if there was a place where we could see where all these events are going on, so we can try to make them. But we have to know about it.
Is the slideshow online?
Pardon?
Don't we put the slideshow online? So all the slides are available.
Well, the trick with Cook Children's, we need to limit the number of folks that are going.
Okay, yeah.
So there's a couple things. It is a hospital setting, and we don't know how many people are going to be there. We want to make sure that there's enough room for the people in the hospital. That's the children and the parents and the practitioners are going to be there. And 2, under 0 circumstances are we taking pictures. Okay, there's HIPAA involved there. The hospital will provide us with images. So if you do come, oh, this is really cool. I'll get a photo. Don't. Please.
Right, and this isn't a public event either, right? So for those of you who don't know, this is Tom Roth with a haircut.
Tom Roth with what?
With a haircut.
I've been going to this lady for 30 years, and I say, just make my head look round. That's all I care about. So there were a few of us out there at Rising Star that mowed. It's all ready for wintertime. We didn't get around to staining the decks this year, but we will next year. The wood's pretty dry, but it's holding up well. So, and this is Charlie Haggard's genius. And he fabricated another part that goes up to the guttering. So now we're waterproof in the 40-footer. Yeah. He spent about 4 hours last week while we were out there, and he took the guttering off the top and fabricated another portion from there to there, and it's quite a work of art. So. And the DOT now is paving all the roads at the state park. Just started last week. So, and we've cleared out 12 miles of trails, and the equestrian area is pretty well completed. Campgrounds are pretty well completed. Most of the structures are completed. So I was out there a couple weeks ago, and we assembled all the trail signs, and the ranger's going to install those on the trails. So things are coming along. So hopefully next year. And so.
Thank you, Tom. And just one thought about the Rising Star. We weren't able to mow the entire field. We found out we had a flat tire on the riding tractor, so what we did do is string trimmed and mowed around all the pads so they're accessible, and if you drop something, you're likely to be able to find it. So that's in good shape. And then we'll go back as soon as this monsoon season ends, and we'll mow the rest of it. Going to the Cross Plains Public Library outreach. Go to the next slide. No events in November or December, so moving on. And George, are you online? Anything to say about the website? Okay, go.
Nothing to report, sir. Just keep an eye on it. If you see anything that's kind of strange or needs to be changed, let me know.
Very good, thank you. And so there's a nice graphic. Thank you, Sam. That's right, it's December's presentation. But their presentation actually is going to be a demo of the Noble Observatory.
Nobody told me that.
Well.
He told me when I got here tonight.
Oh.
Too late.
All right, do we have another slide? There we go. And that's typically our last slide of the evening, where the meeting after tonight's a meeting. It is an event after the meeting tonight. So if you're interested, it's a gathering. Okay, it's a gathering after tonight's meeting at the social house. So I would entertain a motion to dismiss. There you go. Second over there. All right. I'll raise your hands if you're in for. All those against? Okay, unanimous. Thank you.